So welcome to this session of advanced life insurance mathematics. And the idea for today is that we're going to start with a new topic, and we're going to dive into the world of multiple state models. And what we want to see is, or what we want to discuss is, how can we see these multiple state models as a generalization of the life insurance mathematical tools that we've been using so far. So in that sense, it's a very natural continuation of what we've been doing so far with the longevity models that we've been studying. So now we just want to make it more complex in the sense that instead of only making the distinction between the policyholder is alive or the policyholder is no longer alive, you can have all kinds of different states that this policyholder potentially can occupy, right? So that's the idea. If you go to the Toledo site, you will see that from now on, I will follow the book by Dixon, Hardy, and Waters. So if you want to read, if you want to read the story on which these lecture sheets are based, then I can refer you to this book because I'm going to follow the book super closely. So we're gonna tackle. I think it starts from chapter 8 in the book with the chapter on multiple state models. Right. So that's the idea. So here you see these. You see the book cover of the book by Dixon, Hardy, and Walters. So that's also the book that you used in the basic life insurance mathematics course. And essentially, I'm just picking up where Professor Dane stopped, or where you were left with this initial course. If you want to read something else on multiple state models for actuarial work, then I can recommend you the book of Haberman and Pitako, because that's really a dedicated book to this concepts of multi-state models and how to use them, particularly for disability insurance modeling, right? So these are our references, so you know where to find those. And if you don't do, then I suggest that you talk to one of the students who took the life insurance mathematics course already, because they know where to find the book. Okay, so what are our learning objectives for this part of the course? We want to describe what are multi-state models. We want to see the basic survival model that we've been studying so far. We want to see that as, let's say, the most simple example of what such a multi-state model can be. And we want to sketch, of course, in what kind of circumstances, for what kind of problems can you use such models. And then we want to dive a bit more into the mathematics. So we want to derive relevant probabilities. These are typically the probability to make a transition or the probability to stay during a certain time period in a certain state, for instance. And we're going to derive such probabilities by first specifying what are the transition intensities. And the transition intensity, that will be the equivalent of what we called earlier on the force of mortality. So in a basic life insurance model, there's only one transition that matters. That's to go from the alive state to the dead state. So you only have one transition intensity, the force of mortality. But now you're going to have multiple of such intensities, which can matter in these specific problems. So that's what we will work with. And then, of course, our focus is on valuing insurance products. So we're going to look into insurance products, typically for disability or health insurance products, that kind of stuff. And we're going to look into how to value premiums, how to value annuities, how to value insurance products, how to calculate policy values, right? And then if time allows, we're going to see that with the slight adjustment that will be made to the final week of the academic year, because we're not going to do new content in the last week, so we'll see how far we get. But my intention is to also discuss the estimation of these transition intensities in the multiple state framework. Okay. Now, for those of you who didn't take the basic course on life insurance mathematics with my colleague, Professor Dane, you should have some background here about these basic tools, like what is an annuity, what is a policy value, how do I calculate a premium for a simple life insurance product. And you got a recap of this if you took this data camp course that I put together with Rolf Verbelen on life insurance valuation techniques, right? So I'm going to repeat what we need later on, but it's good if you take a look at these concepts yourself, for instance, via the data camp course, and if you have some basic knowledge of these, right? So that's what we want to do. I put one slide here on the use of GLMs because I want to mention or give you a bit of an overview of the different tasks for which we've been using GLMs so far. So GLM is a generalized linear model. So those of you who are with me in the data science course for non-life insurance, they studied the use of GLMs for non-life insurance pricing already extensively. In the part of the advanced life course, the part that we tackled before the Easter break, there we also discussed the use of GLMs to calibrate, for instance, a Lee Carter model, so to calibrate a life metrics model. And now we're going to add one other purpose to this list, and that is the use of GLMs in multi-state models, specifically to estimate transition intensities between the states in such models, right? So that's a nice agenda or a nice wrap-up of these different applications of GLMs that we're gonna encounter across the different courses. Okay, so why do we do that? Or what is the question here? If you look at the use of GLMs, we want to use those GLMs to model transition rates, probabilities in a multi-state model. The advantage of doing it in that way is that you can rely on the foundations of GLMs, on the statistical inference tools, the variable and model selection tools, the available software, and so on, right? So that's our goal. We have to take into account throughout this chapter, so to say, the GLMs will be built for transition rates, transition intensities, and not directly for probabilities. And that the switch from a transition intensity to a probability is not necessarily a trivial task. We're going to cover that today already, right? So in a sense, this is kind of a warning about the use of these GLMs in the more broad context of multi-state models. But in a sense, this should not come as a surprise, because also in the alive debt model, we used the GLMs when we were working with Lee Carter. We used the GLMs to calibrate the model that we specified for the force of mortality. So that's also at the level of the transition intensity. And then having this estimate for the transition intensity, for the force of mortality, we were able to derive an expression for survival probability, probability of dying, etc. Yeah, so keep that in mind. In general, you use these regression type of models to estimate the transition intensity, or to estimate the parameters used in a transition intensity, and then you have to make the switch from this transition intensity to a transition probability. And sometimes that's trivial, but sometimes it is not. Okay? So let me start with this exciting statement. I think it's I'm sure it's a quote from the book by Dixon and Hardy and Waters, and they say, well, multi-state models, that's one of the most exciting developments in actuarial science in recent years. So that's promising for this part of the course. So let us first start with giving a few examples. So what do we have in mind? What kind of settings are we going to work with? So here we go. The most simple multi-state model, like I already mentioned, that's the alive debt model. So we know that from the first sessions in this course, we look then at an individual, say HX, We follow the future lifetime of this individual. We call it Tx, so that's our random variable. Tx will take positive values in continuous time, right? And we could be interested, for instance, in what is the CDF of this Tx, what is the survival function of the Tx, and so on and so forth, right? Now, if you think about this model and you want to sketch or you want to represent this model as a multi-state model, then we should picture this as a model with only two states. We have the alive state, which we label here with a 0, and the dead state, which we label with a 1, right? So typically, the kind of natural state to start with is labeled with a 0 in the book, and then the other states are labeled with a number from 1 up to n, let's say. So what matters is the definition of which states are possible, but also, of course, which transitions are possible between two states. And here that's pretty obvious. Huh? We only allow for a transition from 0 to 1 and not vice versa. And with this transition, you will have a transition intensity or a transition rate. In this case, that would be the force of mortality for my X-year-old and the way how it evolves over time. Right, so that's the basics. That's our very first example of what a multi-state model will look like. We will always draw these models with blocks where we define the different states, and then with arrows, directed arrows, we define the possible transitions between two states. Good. Now, if you think about this survival model that we've been working with in the first part of the course, then you can say, well, let's start from a live hx at time 0, and let's label y of t as the state in which our individual is in at time t. So that's the state that is occupied by our individual at time t. So that means that the y random variable can only take a value 0 or 1 in this case. If the y at time t is equal to 0, it means our individual is alive at hx plus t. If the y at time t takes a value equal to 1, it means that our individual has died before hx plus t. So here that's pretty simple. And it's also clear that we can follow this random variable y over continuous time, right? So taking them all together, we say that the y evaluated in t's, or the y registered over the different time points t, form a continuous time stochastic process. So it's a collection of random variables, and here they take values in continuous time. That immediately brings us to a kind of alternative definition for the future lifetime of our individual x, so for tx, because tx is then going to be the time point at which our stochastic process jumps from state 0 to state 1. So tx, that's the largest value for t that we can find, such that y in t, evaluated in t, or y of t, is equal to 0, right? So that's an alternative definition then for the future lifetime of our individual hx. Okay, makes sense? Questions? So essentially, I didn't do anything. I just took the very simple model that we've been studying so far, but I rephrased it in the context of my multi-state framework. Right? We want to go beyond this, and we want to look at other types of insurance products, and hence also at more complicated models to be understood as models with more states and more transitions, right? Because with this alive death model, you can study products such as a life annuity, you can study a product such as a life insurance, and so on. But what if you would look at a health insurance product or a disability insurance product, or a product where the death benefit is different depending on the cause of death, etc., etc. So as soon as you get a bit more complex products, you will also need to rethink your multi-state model. So in general, a multi-state model is defined by a finite set of states where the arrows indicate possible movements of our individual, our policyholder, from one state to another. Each state represents the status of an individual or a group of individuals. And if you look at the insurance products designed based on such state representations, then the condition for payment relating to this insurance policy could be that you occupy a certain state at a certain time, or that you make the transition from one state to another state. Yeah. So if we think again about these life insurance products that you've been studying so far, if you think about a life annuity, then that is a product that will pay you a certain income as long as you occupy a certain state, in this case, the alive state. But if you think about a whole life insurance product, for instance, then that is a product that pays you a certain, not you, but your relatives, a certain death amount or death benefit if you make the transition from state 0 to state 1, right? So that's a distinction that we make, and we can come up with all sorts of different benefits products based on these two general principles. Good. So let's do some more examples. As you will see at if you look at the numbering of my sections and so on, so that corresponds to what the book is doing, or at least it should be. So you'll see here that I'm super closely following the book by Dixon et al. So what we do here is we look at a term insurance with an increased benefit on accidental death. So you have to see this as an insurance product that pays a certain benefit to your relatives in case you, the policyholder, in case you die within a certain time period. Yeah, so that's why it's a term insurance. So that means the time period during which this insurance cover holds, that time period is specified. So for instance, it can be 20 years or 30 years or whatever. And here in this example, we make a distinction between death because of an accident, and with this event, a benefit amount of 100,000 euro corresponds, and that's because of another cause, and there you get a death benefit of 50,000 euro. So in order to design this, you can say, let's do 3 states. We have the alive state, we have the death by accident state, and we have the death because of other causes state. And what we want, or what we need in order to work with this model, is calibrate the intensity to go from 0 to 1 and the intensity to go from 0 to 2, right? This is a multi-state model. We will also call it a multiple decrement model because it's in fact a setting where you have one starting state and you just look at different exit states. And that's the only transitions, or these are the only transitions that are possible in this framework. So that's an example of a multi-state model. Second example, the disability model. So this is a very important one because this is, of course, an important insurance product, a disability cover that will help you, or that will pay you a certain benefit while you are not able to go to work, let's say. So here we start with a simple version of this model, and it's called the permanent disability model. So here we have 3 states. We have the healthy state, you're able to work, you're active. We have the disabled state, that's state number 1, and we have the dead state, that's state number 2. But the only transitions possible here are from 0 to 1, from 0 to 2, and from 1 to 2. So that is why it's called the permanent disability model, because we don't allow the return from disability to the active state, in this simple example at least, right? So what kind of insurance products or what kind of benefits can you think about? We can think about an annuity that pays while you are in state 1. We can think about a lump sum, so that's a benefit that is paid once on becoming permanently disabled. So that would mean when you make the transition from 0 to 1, a certain amount will be paid. Or you can think about a lump sum that is paid on death. So when you make the transition from 0 to 2 or from 1 to 2, a certain amount will be paid. When are you going to pay? When are you going to pay premiums? You will pay premiums while you are in the healthy state. All right. So this is a three-state model. It's not yet very complicated because we don't allow for these transitions to go up and back, right? So we only allow the transitions here in a single direction. Then if you look, of course, at the next step, that will be the disability income insurance model. So I removed the term permanent here because now I'm going to allow for transitions from 0 to 1, but also from 1 to 0, right? So this is a more natural setting, of course, but mathematically it will also be a more complex model to work with. So here we have the transition up and back between the healthy state and the state of disability. So when you think about a disability income insurance product, you can think of a product that pays you a certain benefit in the periods, during periods when you're sick. You can think about it, and of course this benefit will cease upon recovery. So if you're able to get back to work, the benefit payments will stop and you will pay premiums while you are healthy. You can also extend this product with benefits, lump sums that are paid when you make the transition from 0 to 2, from 1 to 2, and so on and so forth. Okay, so this is a very important one to keep in mind because many of our examples throughout the course and throughout today's session will be based either on the permanent disability model or on this specific disability model. Good. All right, some important features here. We can enter a state multiple times. So we can go from active to disabled and vice versa. That's the example that you see here. We could have several periods of sickness that could occur before death with healthy periods in between, right? So that the possibility to go up and back, that is important. And then the last example that I want to discuss here or want to present here, that's an example that we're going to use to design products, annuity products, insurance products issued to more than one policyholder. Yeah, and these are constructions that you often find in retirement plans and so on. And we're going to treat them here, these multiple life insurance products, we're going to treat them here within this context of multi-state models. Now think, for instance, about a joint life annuity. That would be an annuity product that is that pays you a certain income as a couple until the first death occurs. Yeah, so that annuity goes on until the first death. On the other hand, you can also think about a last survivor annuity. That would be an annuity that is payable until the last death among a group of lives. Yeah, and typically you will have there a rate that is a bit higher when both partners are alive, and that rate will drop, say, to 2/3 of the original rate or something upon the first death of the partners. Yeah, so we're going to spend quite some time on these kind of products as well. So I'm just mentioning them here as examples. You could go a bit further into that. So what is a reversionary annuity, for instance? That's an annuity that starts paying on the death of a specified life if the remaining partner is alive, and that annuity will go on through as long as the surviving partner is alive. So that's, for instance, as part of a pension plan. In Dutch, I would call that een wezenpensioen of een partnerpensioen, for instance. So that is an annuity that starts to pay upon the first death among a couple, and that will go on until as long as the last surviving partner is alive. Yeah. You can also think about insurance products designed for couples or for multiple lives, where death benefits will be paid, for instance, on the first death or on the second death, or whatever you want to design. So how can we treat this as a multi-state model? That's the question. And to clarify that, I'm going to jump to this scheme immediately. So what you see here is that I distinguish 4 states, where in state 0, both partners are alive. And we take here the very classic setting of wife and husband. And then we can go from state 0 to state 1. We can say, okay, then the wife died, the husband is still alive. Or we can go from 0 to 2. Wife is alive, husband died. And then we can go to state 3, where both partners died, right? So here are the transitions indicated, transitions that are possible. Of course, you could wonder, is there a transition possible from 0 to 3? But in theory, that could be the case. Yeah? So that would be the setting where both partners die exactly at the same time. And if we take that into account, then that model is often called in the literature the common shock model. So that's a slight extension of the multi-state model that we had on the previous sheet. So we're going to use this model to study insurance products, annuity products that are issued to more than one life. Yeah, so this is also something that then really extends the work that you've been doing with Professor Dane, because with Professor Dane, if I'm not mistaken, all the products that you studied were issued to a single life. And now we want to be able to extend this to 2 partners, or perhaps to 3 or 4 family members, or whatever you need to put together. Yeah? So that can also be treated with these concepts of multi-state models. I skipped one slide, but I think it's quite obvious. So what we do here is we say let X and Y be the ages of the 2 partners, say the age of husband and wife. When the annuity is bought, then we can denote with our Y, our status variable. We can say Y is 0 if both partners are alive at ages X plus T, Y plus T. And then if Y equals 1, then you go to state 1. If Y equals 2, you enter state 2, etc., etc. Yeah? So that's basically the stochastic process that comes with this 4-state model. Okay, now just to make a slight connection with what you've perhaps seen read in the newspaper, etc., is what about these models used in epidemiology? Yeah, so I just included a couple of examples here, because there you immediately see that these so-called compartmental models in epidemiology have a lot of correspondences with the multi-state models that we study in actuarial science. So a classic model is the SIR model, where we distinguish 3 states. So S is for susceptible, I is for infectious, and R is for recovered. Yeah, so that is really the basic model used or studied by epidemiologists for disease modeling. For disease modeling. And I'm showing it here just to point you at the corresponding items, concepts between the multi-state models that we know in actuarial science and what these epidemiologists are using. So you see the different states, you see the transitions that are possible, and of course you've got a basic model here. So this is like the equivalent of the life-death model for actuarial science. And then you will also see that people have been adding different states, adding different transitions, just to make sure that they've got a model that is compliant with the modeling approach that they want to take. right? So here as well, it's about estimating the transition intensities. It's about estimating the number of people in each compartment, given that you start from a certain specified population, right? I put one extra here. That's the SEIR model, where S is then for susceptible, E is for exposed, so that would mean that you are infected, but the disease is not yet making you infectious. So that's during the incubation time. So you are already infected, but the symptoms of the disease are not yet are not yet shown, are not yet noticeable. Then I is again for infectious and R for recovered. And you can design way more compartmental models. I mentioned a few of them over here. So you can, instead of having the recovered state, you could also add a dead state. So that's with the D over here. You could go for a cis model. So then you go from susceptible to infectious and back, and so on and so forth. So it's all about designing suitable states and defining the possible transitions between these states. So here we have a nice analogy between the disease models which are currently used to model COVID-19 infections and the tools that are used in actuarial science. Good, so if that makes sense, then we're ready to dive into a bit of notation and a bit of derivations for the transition probabilities and transition intensities, right? So we started off with looking at a lot of different examples of what these multi-state models can do for us. So what we now want to focus on is introduce some suitable notation and name a few assumptions that will allow us in the next steps to do some calculations with these models, right? So first of all, we start with n+1 states. We label them, at least that's what the book does, and that's what we will follow. We will label a sort of basic state with 0, and then from there on, we will label the other states from 1 to n. We assume that instantaneous transitions are possible between selected pairs of states. So in general, this means, in general, we start with continuous time, right? And we're later gonna simplify to discrete time transitions and so on. But in general, let's say we take the framework of continuous time transitions. Our random variable y will take a value between 0 and n and will register, okay, at time t, which state do you occupy? So that is a random variable because we don't know upfront which state you will occupy at time t. So yt is equal to I means that you are in state I at time t. And at time t here corresponds to age x plus t. Yeah, so that's a typical actuarial setting, which you all already used in the life insurance mathematics setting or case. At time 0, we assume that our policyholder has hx. So when we go to time t, we have an x plus t year old, and so on and so forth, right? So when you draw timeline, it's often good to put there the age as well as the time so that you are sure what kind of which kind of axis you are using. So we already mentioned yt. If you collect all the y's over time, you have a continuous time stochastic process because you have a collection of random variables over time. So that is our setting. And we're going to look at insurance, we're going to look at annuity products, and we're going to look at products which where the payment depends on either being in a given state or taking a move, so a transition between a given pair of states at a given time. And that's what we're going to tackle with these multiple state models. Yeah, so that's important to keep in mind. Also later on, when we have to value certain products, you always have to think for yourself, okay, should I value this component as an annuity? Is it something that is paying me while I'm in a certain state, or should I value this component as an insurance product? That is, am I gonna will this benefit amount will that be paid when I make the move between certain states? All right. So we need a few assumptions, and this sheet number 22 comes back to Jonathan's question, in fact, because our basic assumption that we're going to make to get started is that for any states, I and j, and any time points t and t plus s, say, the probability that y at time t plus s is j, given that y at time t is I, that probability should be well defined in the sense that the probability cannot depend on information about the past of this process, so about the process before time t. Yeah. So you can also say that the probabilities of future events should be completely determined from the current state. That's a Markov property, and so we're going to work here with a Markov process. So I'm saying that's coming back to Jonathan's question, because Jonathan said, yeah, but shouldn't you take the time spent in a certain state into account when you're thinking, for instance, about the transitions out of the disability state? Huh? And that's very true, but it would not be compliant with the assumption that we're making at this point, right? So what are we going to do in the next classes in order to be able to tackle that? We're going to split a state, for instance, a disability state. We're going to split it in several substates so that we can take the time spent in a certain state into account just by differentiating these disability states. For instance, yeah, you can be disabled in the first year, disabled in the second year, and so on and so forth. Yeah. So you have to be a little bit careful with that. Our basic assumption for our toy examples will rely on this Markov property, sorry, but don't worry, we will be able to give it a tweak if we need it, and if we want to take the time spent in a certain state into account later on. But that will come, that will come. Okay. A second assumption is that for any interval of positive length h, the probability to do 2 or more transitions within a time period of length h is little o of h. And now this concept, little o of h, what does it mean mathematically? So a function j is little o of h. If this limit with h running to 0 of g of h divided by h is 0. So what does that mean intuitively? That this g function, or this little o of h function, is going to 0 fast enough, right? So for a small interval of length h, the probability to have 2 or more transitions in that interval is so small that we can ignore it in our calculations. Yeah. So that's what we mean here, and that's something that we will use in the derivations that will follow today. So maybe before we take a break, let's revise some traditional notation that we know from the life insurance mathematics course. So in this life insurance mathematics course, we've been working with TPX, TQX, MUX. So to fresh up your mind, the TPX, that's the probability that an X-year-old will survive until age X plus T. TQX, that's the probability that an X-year-old will die before reaching age X plus T. And MUX was the force of mortality at age X. So my point here is, how can I generalize this notation such that I'm able to take these multiple states into account? Yeah. And what we're going to do is we're going to label our notation with I and J, where this I and the J refers to the two states that we want to take into account. So for instance, TPXIJ, That would then be the probability that given that you were occupying state I at time 0, and time 0 corresponds to hx, what is the probability that you will occupy state j at time t? And time t corresponds to hx plus t. Okay, so that is what we're going to call a transition probability, the tpx ij. And now we have also a specific type of probability that we also want to introduce, and that's the probability that we stay in a certain state during a certain amount of time. And we're going to call that in English the sojourn or the occupancy probabilities. So in Dutch you could say de blijfkans, de kans dat je in een bepaalde staat gaat blijven. And that's what we're going to denote with I with a bar. Yeah. So it means given that I started in state I at time 0, what's the probability that I will be in state I at time t? But what's the probability that I will have stayed in this state I for the whole duration of the interval between 0 and t? Yeah, so that's why I have the notation here for all s, where s is between 0 and t. So I didn't leave state I. What is that probability? Yeah, so that's a very important notation to keep in mind. And this sort of generalizes the more classic actuarial notation with the P's, with the Q's, with the mu's that we've been studying or we've been using so far. Okay. So here is my explanation, TPXIJ. I explained that TPXII bar. So the underlined word here is very important. The probability that you stay in state I throughout the whole time period. In this case, from hx to x plus t. Let me just then make the analogy with the TPX, the TQX from before. And I'm going to do that over here. So I'll get back to the previous sheet right away. So of course, if you look at the alive-dead model, we had state 0 is alive, state 1 is the dead state. So what we have then is that TPX00 is the same as our classic TPX as we know it. And of course, that's the same as TPX00 bar, right? Because in the simple alive-dead model, staying in state 0, whether you denote that without a bar or with a bar, that's the same because there is no transition possible that will lead you out of state 0 and allows you to come back to state 0, right? TPX01, that would be the equivalent of TQX. That's the probability that you die before age x plus t. Okay, that's the analogy that I wanted to make. An extra point is then, of course, what is the force of transition? That's the mu xij, because now, of course, you also have to specify what kind of transition are you making from state I to state j, and we define it as the probability that you make this transition between hx and x plus h divided by the length of the considered time interval, in this case h, and we then take the limit if this time length is going to 0, right? So we consider a transition from I to j in a very small interval of time. So given that you occupy state I at hx, what's the probability that right after reaching hx, you will make the transition to state j, okay? And that is, of course, the equivalent of or it's a more general version of the force of mortality as we've been introducing it so far, because with the force of mortality, you would only look at the transition from state 0 to state 1, and then we defined it in exactly the same way as what you see over here. Yeah, so the mu is the force of transition or the transition intensity between states I and j. We're going to assume that it is bounded, that it's we can take the integral of this mu, we'll need that later on, And we're also going to assume that the TPXIJ is differentiable, because that's also something we will.
So what did we do before the break? We essentially motivated the use of multiple state models in actuarial science, and we looked at a couple of basic examples of what such multi-state models could look like. And we emphasized that what we're interested in is either an insurance product that pays you a certain income while you are occupying a certain state, or a product that pays a benefit, a lump sum, if you make a transition from one state to another. And in order to value such insurance products, we'll need to have a probabilistic framework that allows us to express, okay, what is the probability that, given that you start now in a state I, what is the probability that in a time period with length t from now, you will be in state J, let's say, and that kind of stuff. Okay, so we introduced our notation. Let me go back to this expression. So we introduced a notation Pij to denote the transition probability from state I to state J. And we introduced the mu ij to denote the force of transition, or the transition intensity, to go from state I to state J. Now picture this formula that you see over here. That's the definition of what a rate will be. So you look at the probability that a certain event will happen over a certain interval of time. You divide by the length of this interval, and you let the length of this interval go to 0. All right? So rephrasing this expression, and now I'm here on my sheet. So if you rephrase this expression, you can also see the transition probability to go from I to J in a length of time equal to h. You can also rewrite that as follows. So that's nothing but the definition from the previous sheet. How can you see that? Well, divide the whole thing by h. Take the limit for h running to 0. Then this little o of h will disappear. It will become 0. And then you're left with the definition of the transition intensity as we put it on the previous sheet. Yeah, so this is exactly the same. Same definition, but this brings us some intuition, namely that for very small and positive values of h, we could say that this probability to make the transition from I to j in a length of time equal to h, that is approximately equal to h multiplied with the transition intensity. Yeah? So that's some intuition that we can gain from this expression. All right? Okay. So what we're going to do now is we're going to look at a series of examples, properties, etc. And the whole goal of working through these different set of examples is to derive some very general expressions for the transition probabilities, which can be used then in our further calculations. So first of all, a simple example, 8.1, where we're going to look at the difference between the expression that you see here at the left-hand side of the equation and the expression that you see here at the right-hand side of the equation. So remember what this bar notation was about. If you look at the expression with the bar, then it means that you're going to stay in state I. So in this case, I'm referring to the probability that somebody who starts in state I at hx at time 0 will still be in state I at hx plus t. Yeah, so this is what we call the sojourn probability. This is the probability of staying. Whereas here, if I look at the left-hand side, then I'm referring to the case where you, or the events, where you start in state I at hx time 0, and at time t, hx plus t, you are again in state I. But this includes the possibility that you left perhaps state I and went back. Okay, so that's a difference between these two probabilities that you see over here. So why can we say that they are up to a term little o of t, that they are the same? Let's think about these probabilities and about the differences in events that they represent. So we explained what this occupancy probability is. We explained what the other probability is about. What does that imply? This implies that the sojourn probability has to be smaller than or equal to the more general transition probability TPXII. Why? Because of course, the event in which you stay in state I is included also in the expression on the right-hand side here, the TPXII. But this probability also captures alternative situations, events, where you left state I and just went back before time t, right? So this ordering must be satisfied. And if there is a difference between the two, then that difference is caused by those events, by those paths where the process made two or more transitions between hx and hx plus t, yeah, so that it made sure that it is back in state I at hx plus t, right? So in order to start in state I at time 0 and again be in state I at time t, that would mean that you make at least two moves in an interval of length t, and we know by assumption number 2, I think, we know by assumption number 2 that this probability of doing two or more transitions in an interval of length t, that is little o of t, right? So that explains the difference here between the left and the right-hand side. Okay, yeah. So that's the first example, and we'll see more of these examples, which will force us to think a little bit about these concepts and to come up with meaningful expressions to work with these different transition probabilities. So that was example 8.1. Let's continue with another one. So what if we think about an expression for these sojourn probabilities? So again, we're looking here at the probability that given that you start in state I at hx times 0, what is the probability that you will still be in state I at hx plus h without ever leaving this state I? And you'll see here a first expression coming up, which we will need to derive a more general expression for this probability of staying. So let's look first at this expression. Okay. So what am I going to do? I'm going to look at it in the following way. So I'm going to look at the complement of this probability of staying. So I'm going to look at 1 minus the probability of staying. So that is the probability that the process does leave state I at some time between ages x and x plus h. Possibly it is returning to state I before hx plus h, but that doesn't have to be the case, right? So we look at the complement of this probability of staying. Okay, so basically I bring the one to the other side, or I bring this guy to the other side, and then this whole thing to the other side. Yeah, I flip around. Now, if the process leaves state I between hx and x plus h, then it must be in some state j different from I, or it must be in state I, having made at least two transitions in a time interval of length h. Yeah. So what does that mean? If we look at, if you don't stay in state I, then there are a couple of possibilities. So then it means that at hx plus h, at time point h, you will be in some state j which is different from I, or perhaps you're back in state I, but then at least you made two transitions. Yeah. So the probability to do the first thing, so the probability to make this transition from I to j in an interval of length h, that would be h px ij, right? But about h px ij, we said, yeah, that's approximately equal to h multiplied with my force of transition. And that's one of these intuitive expressions that we just derived. So you'll get, if you take the sum over all the j's that are different from I, you'll get this probability, the total probability that my process will leave state I and will be in some state j different from I at time h, right? And next to that, if you say, yeah, imagine that you're back in state I at hx plus h, then you should have made at least 2 moves, and that probability is little o of h. Yeah, so that's how we can see that the expression here at the top is a valid expression. So that's a lot of words. I'll try to do some more handwriting for the rest of the class. But I think if you carefully read this and if you think about it again, then this makes a lot of sense. We're simply using the assumption or the expression that we put together over here, right? So that's my number 3. That's essentially what we're using here for j different from I. Okay, good. So that was section 8.3. So what did we do in section 8.3? We put together a meaningful notation to be used in our framework. And we introduced the concepts of transition probabilities, transition intensities. And we made a few assumptions, like this Markov property was one of them. This probability that if the fact that the probability to do at least two moves in a small interval of time is negligible, and so on and so forth. Yeah. And now we're really ready to come up with interesting expressions for our transition probabilities. So that's the goal of what we will cover from now on. Any questions or feedback? Okay, so let's continue then. So what we'll do for now is we're going to assume that the transition intensities are known. And I put here in brackets, is that realistic? No, of course, it's not a realistic situation because it's very hard to come up with meaningful numbers for what these transition intensities will be. Typically, we have to estimate those transition intensities from historical data where we observed, okay, out of a group of people, how many made the transition, for instance, from active to disability, at what age, etc., etc. Yeah, so you would start from a historical data set where you observe the transitions, and from there, using your tools of GLMs, etc., you would be estimating transition intensities, and once you have those, you can use them and plug them in expressions to get transition probabilities. And that's the strategy that we will follow. So today we will only answer the questions if I have the transition intensities, then how can I use them to come up with transition probabilities? And I will assume that I know my transition intensities. Okay, so that's a very important statement here. All the relevant probabilities can be expressed in terms of my transition intensities. The mu xij's, where I'm going to assume that I is different from j, that's important because we're really looking at making a move from I to j, so I and j must be different. These are really fundamental quantities in this whole framework. And you also see that in the epidemiological models, also there the transition intensities are very important to monitor the dynamics of the disease, let's say. Yeah. So these are fundamental quantities. This is typically what we want to estimate from data. And that's also the way how we did it In the first part of this course, there we also looked at the number of deaths out of a given exposure to estimate the force of mortality. And once we estimated the force of mortality, once we had the mu x, we were able to transform it into a survival probability or a probability of dying. So we took exactly the same approach there. Right. Now here is a very important first definition, and that is this probability of staying in state I between hx and x plus t can be written as the exponential of minus the integral from 0 to t of the total force of decrement, let's say. And this total force, that's the sum over all j different from I of the transition intensities mu ij at hx plus s, and then you take the integral over all time points s between 0 and t. Yeah, so that's a very important first expression, and we're going to derive it right away. Yeah, but I hope you immediately see the analogy with what we had in the first half of the course, because there we set the probability of surviving between hx and x plus t. That was the exponential of minus the integrated force of mortality. Yeah, so that's exactly the same kind of structure. But here, of course, if you look at somebody who is in state I, then he can leave he can go to any state j, which is different from I, and there are typically multiple states that we have to take into account. That's why we look at the sum of all the applicable mu ij's, where I is different from j, and where the force, the intensity, is different from 0. Yeah, so this is an important expression, and you may also see immediately the connection with what we had on the previous sheet, because on the previous sheet you have a kind of first order approximation of this exponential function being put over here, right? Where we assume that we get rid of the integral by assuming that our forces of that our transition intensities are piecewise constant, such that we get the h in front of the sum of the transition intensities. Yeah, so that's a bit the connection between number 5 and number 6. Okay, so how does that work? I'm going to look at the expression that tpx ii bar is equal to the exponential minus the integral from 0 to t, the sum over j, where j is different from I, of mu x plus s ij, and I'll take the integral over s. Yeah. So what am I going to do? First of all, so this is the probability here of staying in state I from time 0 to time t. Yeah, and what I'm going to do, I'm going to start, in order to derive this expression, I'm going to start with the probability t plus h, px ii bar. So that means that my policyholder stays in state I in the period from 0 to t plus h. Yeah. Given that you are in state I at time 0. And time 0 corresponds to hx. So what we're going to do now is we're going to draw a timeline. And we're going to look at what can happen during this period of time that we consider. So here you have hx at time 0, and we're going to go up to hx x plus t plus h at time t plus h. And we're going to see what is happening in between. So what is happening at hx plus h at time h. So we want to know what's happening here. Yeah. So we can make, or we're going to split this thing into two sub-events. So we're going to say you have to stay in state I. In the interval from 0 to, yeah, sorry, I'm going to switch to notation t here. That's how it was meant to be. So this should be a t. And I'm going to focus on the sub-event where I'm staying in state I between 0 and t. And then I'm going to look at staying in state I from t to t plus h. So, yeah, let's make this an interval like this. Okay. So what do I know following the multiplication rule that we discussed earlier on? And I know that the probability that my x-year-old will stay in state I over the whole time length is the probability that he or she will stay up to time t. And then given that you are hx plus t, you will have to stay another time period of length h. Yeah? So that's in fact the multiplication rule, which we already used in the life insurance setting. That's the multiplication rule being applied over here again. But now what are we going to do? We're going to look at this, this expression here. So what's the probability to stay over an interval of length h in state I, given that you are x plus t years old? What we're going to do here is we're going to use the result of example 8.2, right? And if we put that together, then it means that we're looking at the following expression. So that was 1 minus h, and then the sum over j, different from I, of mu x plus t. And then you've got I j plus little o of h. Yeah? So here I'm using the expression that we put together in example 8.2. Now I want to show you this because we're going to do a small rearrangement, which will happen a lot throughout this chapter. So when you rearrange the expression, you'll get to the following one. So I'll bring the TPX I bar, I bring that to the other side. Yeah, I'm going to divide the whole thing by h. Voila. And then I can say, well, that's being equal to minus TPX I bar multiplied with the sum over j, different from I, of mu x plus t ij, plus little o of h divided by h. Yeah. So notice that here the h disappears because I've got the h over here and I'm dividing by h, so I'm left with this expression. And now, of course, you see what I'm about to do. We're going to take the limit for h running to 0. And what you will then see if you take this limit everywhere is that you come up with the derivative with respect to t of tpx I bar, which is then equal to minus tpx I bar multiplied with the sum over j, different from I, of mu x plus t ij. This guy here is going to disappear because if I take the limit for h running to 0, then I'll get 0 with this little o of h term. Okay. If I further rearrange the expression And if I bring this guy to the other side of my equation, then I'm left with the derivative with respect to t of the logarithm of tpx I bar is equal to minus sum over j of this expression. Yeah. So putting it all together, if I would take the integral from 0 to t, if I take the integral, then I'm finally left with the expression as I want to have it. Then I'm left with the logarithm of tpx I bar, which is equal to minus the integral from 0 to t sum over j mu xr like this, and the j should be different from I. So putting it all together, I've got my final expression for the probability to stay in a certain state as the exponential of minus the integral of what we call the total force of decrement. So that's the sum of all the transition intensities that are applicable to state I. And this one is a very important one. So here we are. That's what we went through together. So that's a very important first expression to keep in mind. So there we are. Now, a first expression. At least we can calculate the sojourn probability by integrating over the sum of the applicable transition intensities, putting a minus in front, taking the exponential. That's what this sojourn probability is about. Good. So let us continue, and we're going to continue with a specific example for the permanent disability model. Yeah. So recall for the permanent disability model, what you have there is a state 0, where you are alive and healthy. You have a state 1, where my policyholder is disabled, and you have a state 2, where the policyholder died, and the only transitions possible are from 0 to 1, from 1 to 2, and from 0 to 2, right? That's the setting that we have in mind. So let us look at this specific example. So it's an example with a couple of steps, and eventually the goal of this example is to derive an expression for a transition probability of this type. So a transition probability where I have as the superscript 0,1, for example. So I'm not dealing with an occupancy probability, but with a more with a different type of transition probability. So first of all, we want to see, or we want to understand, that the following expression makes sense. So let's start from there. And we're going to look here at the t plus h px 0,1. So that means, given that I start in the healthy state at hx, what is the probability that I will be in the disabled state at hx plus t plus h? Yeah? And we want to wonder how we can see this guy using the following expression. I think it feels like it's going to be more easy if I write a bit more. So let us do this together, because otherwise I have to read a lot of formulas out loud, and that's not always easy. So let's continue with our derivations. So what can I see here? I want to start with looking at t plus h px 0,1. And I'm going to look at the permanent disability model, where I have transitions like this. Okay, so that's the multi-state model that I want to consider. So what am I going to do? I'm going to draw a timeline again, where I look at hx at time 0, where I'm going to go up to hx plus t plus h at time t plus h. And what I'm going to do, just like we did before, is I'm going to look at what's happening in between, say, at time point t with hx plus t. So where am I at that particular time point? Now, there are two scenarios. There are two scenarios for the state that my policyholder can occupy at time t. So either you are, and that's the first scenario, either you are disabled at time t, right? And that's going to happen. If I look at my timeline, that scenario is going to happen with a probability tpx 01, okay? And if you are disabled at time t, we have a policyholder who is in state 0 at time 0. And we want to know what's the probability that you will be in state 1, the disability state, at time t plus h. And we're going to distinguish, okay, what's going to happen at a time point t in between. Which state are you occupying then? So if you are occupying at time t the disability state, then that means that you made the transition from zero to 1 in this interval of length t. And that also means if you need to be in the disability state at time t plus h, and that means that you're going to stay here with probability h px plus t 1, 1, right? So in this case, I've got a scenario that's unfolding with probability specified like this. Okay, so that is the first type of event, or the first scenario that can be possible. On the other hand, if my life would be healthy at time t, hx plus t, yeah, then what is the probability that in this scenario that I will end up in the disability state at the end of my interval? Well, then I can say that scenario or that event is going to happen with a probability I first stay in the healthy state, yeah, between hx and x plus t, and then I'm going to make the move, yeah. I'm going to make the move to go from the healthy state to the disability state between hx plus t and x plus t plus h, yeah. And for this latter probability, this guy, we know by one of the assumptions that we made earlier on, and one of the examples we tackled earlier on, that we can write that as such. Okay, so in total, if I put everything together, I can say in the permanent disability model that the t plus h px 01, that is equal to tpx 01 multiplied with h px plus t 11 plus tpx 00 multiplied with my h mu x plus t 01 plus a little o of h. And that was exactly the expression that this example asked us to look into. Yeah. So yeah, once again, sorry for the interruption, which sort of broke my explanation and my concentration. But what I'm doing here is I'm gonna start with somebody hx in state 0, and I'm gonna wonder what's the probability that you will end up in state 1 at hx plus t plus h. And I'm going to write this probability by distinguishing what's going to happen at some intermediate time step t. Yeah, and I will distinguish what if you end up at time t in the disability state, what's going to happen if you end up at time t in the healthy state. These are two distinct scenarios. These are also the only two things that can happen. So the requested probability can then be written as the sum of these two probabilities. Yeah, so that's the reasoning over here. Okay, so this is the expression that we just showed, that we took a look at. Do note the bars that I have over here. I can also leave them out because there is no way I can leave state 0 and come back, right? Because we're dealing with this permanent disability model. Now we're going to go a bit further in this derivation, and what we're going to do is we're going to manipulate the expression so that we can end up with the expression that is shown over here. And again, eventually this will lead us to a more intuitive expression of what this transition probability, the TPX01, what it will be like. Yeah. So what are we going to do? We're going to take the previous expression. So we're going to take our example from here, our expression from here, and we're going to say, yeah, this probability to stay in state 1. Well, I can see that as I can see this. Let's see. I can see this as 1 minus h times the transition intensity, the mu1, 2. Okay. Yeah, sorry, I'm completely, I lost my concentration a bit, but voila, that's what I just derived. So I want to manipulate this expression a bit more. And I'm first going to look at the occupancy probability that you see over here. It's this one. And I know that I can write this guy using the example that I covered earlier on, that I can write it as 1j, let's say, where j is different from 1, plus a little o of h. Yeah? This was what I derived in example 8.2. And now, of course, I have to keep in mind that I'm looking at this permanent disability model. So I only have 0, 1, and then 2, right? So if I look at what different transition intensities that I can use here, yeah, that means that I can only take into account the transition intensity to go from 1 to 2. So this expression reduces to 1 minus h times mu x plus t 1, 2 plus little o of h. And that's what I'm going to plug in the expression that I started with. So I've got t plus h, px01 is tpx01 multiplied with 1 minus h multiplied with my force of transition to go from 1 to 2 plus little of h. And then I've got as well the remaining terms. That's the tpx01, 0, bar, and then the h multiplied with mu x plus t 01 plus little of h. Yeah. What am I going to do now? Same operations as before. I'm going to bring this guy to the other side. I'm going to divide by h, and I'm going to take later on also the limit for h running to 0. So what I get over there is, by rearranging, I'll find the expression t plus h tpx01 minus tpx01. I'm going to divide by h right away. And I'm left here with minus h, no, sorry, I'm going to divide by h right away. Yeah. So let me bring this to the other side as well. So I'll get something like this is tpx 00 bar multiplied with mu x plus t 01 plus little of h divided by h. Okay, so if I take the limit for h running to 0 at all sides of the equation, then I get that I'm left with the derivative with respect to t of tpx01 plus tpx01 multiplied with mu x plus t 12 is equal to tpx00 bar multiplied with mu x plus t 01, because the limit of this little of h divided by h, that's going to be 0. I'm almost, well, not almost, but I'm now going to work towards the expression that you had on the sheet. So what am I going to do? I'm going to multiply both sides by the exponential of the integral from 0 to t of mu x plus s 1, 2, right? So if you do this, then you can put the whole thing together by saying that's the derivative with respect to t of my tpx01 multiplied with my exponential, like this. And that's going to be equal to my tpx00 bar mu x plus t 01 multiplied with this exponential, like this. So what did I do here? I took a couple of things together because here I've got the derivative of the product of my transition probability and then the exponential of this integrated transition intensity. So if you would work out this derivative, yeah, what you should get then is the expression that we have on top multiplied with this exponential thing. Yeah, so you can see that if you would work out this derivative. You can clearly see that it's been a while since I've been teaching. And I didn't sleep very well tonight, the past night. So all of this together creates this kind of mistakes. So sorry for that. But what we have is then, if I work out the derivative with respect to t, tpx01, multiplied with my exponential guy, plus then tpx01. And what I would have to do now is take the derivative, take the derivative of this exponential function. Yeah, so that's the exponential function itself. And then, because of the chain rule, I would have to take the derivative with respect to t of the integral from 0 to t of this force of transition between 1 and 2. So what I'm going to do there is use the hoofdstelling, the main theorem of calculus. So you get there the mu x plus t 1, 2, right? And that's essentially, that's exactly what we need, or what we would get if you look back at the point where we started from, because we started here with the expression at this side, and we said, yeah, do the multiplication with this exponential. And then immediately I said, yeah, that reduces to the derivative that you see over here. And that's true because if I would write that in full, then indeed I get the expression that I started with, top of the sheet, multiplied with this exponential function. Yeah. So there is an equivalence between the things that I'm going to put in blue. If I work out this multiplication, the two of them together, they lead to the expression below here in blue. They lead to what I got over here. Okay. So that being said, we still need to do a couple of steps. This is a bit of a complex example to get started. Because now what do I have? I have that the derivative with respect to t of tpx01, and then my exponential guy, right, is equal to tpx00 bar mu x plus t01 multiplied with the same exponential stuff. Okay, so what am I going to do now? I'm going to take the integral at both sides from 0 to 2. So from 0 to u. Okay, so if you see at the left hand side, I'm going to take the integral of this derivative thing. Yeah, so that is going to be u px01 multiplied with the exponential integral from 0 to u of mu x plus s12 ds. And that will then be equal to the integral from 0 to u tpx00 bar mu x plus t01, and then my exponential integral from 0 to t mu x plus s12 ds. Yeah, and this is going to be an integral with respect to t. So here I am, almost there, because now we're going to divide both sides by this expression. Yeah, so we're going to make sure that we get rid of what is here underlined in red. So we're going to divide by that and conclude that I then have the u px01, which is equal to the integral from 0 to u of tpx00 bar mu x plus t01. And then here, of course, you are dealing with the exponential of the integral from 0 to t of this mu12. And you're going to divide it by the exponential of the integral from 0 to u, right? And we're going to assume that this u is larger than the t, of course, because we take this integral from 0 to u of something that is changing in t. So if you work, if you look at that and if you work that out, you're left with the exponential minus the integral from t to u of mu x plus s12 ds, and that's the integral over t. Yeah. So how do I get this last part here? That's by taking this guy divided by this guy. Yeah, and under the assumption that the u is larger than the t. So if you look at this, expression, this guy, then this must ring a bell. And what we have here is in fact the probability that an x plus t-year-old will stay in state 1 over an interval of length u minus t. Yeah, that's what we got over here, because we're dealing here with an interval of length u minus t, and we're going to look at ages from x plus t to x plus u. Okay, and we're taking the integral of the force of intensity to go from 1 to 2, put a minus in front and an exponential. So that's exactly what we meant with this transition probability. So putting everything together, you've got a very intuitive and a very relevant expression as well. This is my u px01 And I can write it as the integral from 0 to u of tpx00 bar mu x plus t 0, 1, and then u minus t px plus t 1, 1 bar. Now this may look, the whole derivation was rather lengthy, etc., etc. But now we can picture a timeline that gives us a lot of intuition about what we're doing here. And we're looking at a timeline from 0 to u. We put a point t and t plus dt in between, right? T is smaller than the u. We look at an hx and an hx plus u, and we put an hx plus t, x plus t plus dt in between. And what we want to know now is, what is the probability, the u px01, what's the probability that you're gonna go from state 0 to state 1 over this interval of time. And essentially what we're saying now is that you're gonna stay in state 0 for an interval of length t. Then when you reached hx plus t, you're gonna make the transition from 0 to 1. And then you're gonna stay for the rest of the interval, you're gonna stay in state 1. So that's essentially what we're saying. And this part here in between, and that's what for this guy we said, that's essentially equal to the transition probability to make this transition from 0 to 1 in an interval of length dt. So that's why I put my dt here as the subscript of this transition probability. That's one of the assumptions that we made earlier on. Then where is this integral coming from, the integral over t? Well, essentially we say this time point t at which you make the transition from 0 to 1, that can be put anywhere between 0 and u. Yeah, but it should happen at some point t between 0 and u. And essentially what we're doing then here is, in order to make this transition from 0 to 1, you're gonna stay in state 0 up to a certain time point, then do the transition in a very small interval after reaching hx plus t, and then you're gonna stay in state 1 for the rest of the considered time interval. Now, of course, and that's very important to emphasize, this is a very elegant expression, but it only works, it's only valid if you cannot go back, in this case, from state 1, for instance, to state 0 and come back to state 1. Yeah, so it really assumes this approach that we take over here. It really assumes that you're going to go from state 0 at a certain point in time to state 1, and you're going to stay there for a while. If movements are possible up and back between state 0 and state 1, then this expression would of course not be valid. And the same holds if movements would be possible from state 1 up to state 2 and up and back, then this would not be a valid approach to take. But first, there is some work to be done. There is some work to be done, and my remaining ambition is that I need to come up with a very general expression for my transition probabilities that holds for any kind of multi-state model that I can come up with. Because the previous expression we derived was very intuitive, but only valid if you cannot go up and back between states. Yeah. And this will lead us to the following idea. So I want to look in general at, let's say, a transition probability of the following type. And I'm going to assume, well, not necessarily, I and j can be the same state, can be different. All these scenarios are possible. Yeah. So what I'm going to do is I'm going to look at this transition probability, and I'm going to take again the approach with a timeline, where I say that at hx times 0, and I'm going to consider here hx plus t plus h. And now all of you are thinking, of course, when will she eventually register for this app that she is using? I should do that. I always forget to do it, but it should be done. It should be done. I hear you thinking. Okay, so here we are with our timeline. And again, I'm gonna put this event at time t in between, and I'm gonna wonder like what's happening at time t, and I'm gonna use this the possible events that are the possible things that are the things which can possibly at time t. Yeah. So here we go. I want to know what is t plus h pxij. What's the probability that I start in state I at time 0, and I want to be in state j at time t plus h, right? So what can happen in between? Well, in between, I can be in state j, right? So I'm going to make a distinction between two possible events. So let's say that I'm in state j at time t. Let's say that I'm in state j at time t. And the second sub-event that I want to distinguish is, let's say that I'm in a state k, which is different from j, at time t. So these are the two events or sub-events that I'm gonna distinguish. Okay, so if I'm in state j at time t, yeah, how do I get there, and how do I continue then with ending up in state j at time t plus h? So the probability of this track, let's say, is equal to tpx ij multiplied with h, and then you do px plus t jj, right? So if I start with looking at this transition probability, and I say, well, at state j, at time t, you occupy state j, then the path that you take from I to j is going to happen with this probability, because it means that you then need to make a transition from I to j in the time interval from 0 to t. And then given that you are in state j at hx plus t, you should again be in state j at time x plus t plus h. Now, so that's my first possible trajectory, if you want. And on the other hand, if I'm occupying a state k that is different from j at time t, then this transition that I'm interested in is going to happen with a probability tpx ik multiply then with h px plus t kj, right? Where the k is now different from j. But of course, I can have multiple state k's, which are different from j. So I should put a sum here in front, and I should take the sum over all the state k's which are different from j. So I go from 0 to n, but I won't take state j into account. So if I put these guys together, if I take the sum of the probability here for scenario 1, if I take the sum for scenario 2, these are distinct scenarios. These are all the only scenarios that can happen. That all together would give me this transition probability. Yeah. But what I want to do with that is I want to bring this back to an expression that is using the transition intensities, because now the only guys that I'm using here are the transition probabilities. But I know that the real stuff is happening at the level of the densities, and so I'm going to manipulate my expression such that I can work in a meaningful way with this. So what am I going to do? I'm going to use our earlier derived expressions, namely number 4. And number 4 was about TPX, say, II is equal to TPX II bar plus little o of t. Yeah. What am I? Oh, yeah, and then I'm going to combine that with the next step, and that is that, say, H Px II bar is equal to 1 minus H, and then the sum over J, different from I, of mu x ij plus little o of H. And so these are the two concepts, or these are the two expressions that I wish to combine, and I'm going to use them to replace the expression that I have over here. Okay, so to replace this guy, I'm going to rely on two expressions that we derived earlier on today. So where does that lead me? That brings us to my t plus h px ij, that's the one I was interested in, can be written as tpx ij multiplied with 1 minus h, and then the sum for k different from j, of mu x plus t jk plus little o of h. And then I had the sum, again for k different from j, of tpx ik multiplied with h multiplied with mu x plus t kj plus little o of h. So what did I do here? I used, or I recycled the expression that I had over here, yeah, but I replaced this guy with my my expression derived over here, and here I replaced this guy with what I've been using earlier on. So maybe I should note that as well. So here I said this guy is approximately, or can be seen as h multiplied with mu x plus t kj plus little o of h. That's also one of the expressions that we derived earlier on today. So if I put all of that together, I get an expression like the one that you see here. And of course, as usual, we're going to rearrange the whole thing. And where does that lead us to? T plus h px ij minus tpx ij divided by h. And that's then going to be equal to minus the sum over k different from j of t, yeah, with a minus, tpx ij multiplied with mu x plus t jk. And then I've got the sum over k different from j of tpx ik multiplied with mu x plus t kj plus 1 little o of h, because I've got 2 little o of h over here, but of course taking them together reduces to. So what you see over here now is, of course, if I take the limit for h going to 0, that then you obtain the following result that says, if I take the derivative with respect to t of tpx ij, then I'm left with the sum over k different from j of tpx ik multiplied with mu x plus t kj minus tpx ij multiplied with mu x plus t jh. And this is what we call the Kolmogorov equations, or the Kolmogorov forward equations, that will allow us, if we can solve this set of differential equations, to come up with with an expression for general transition probabilities of this type in any multiple state model. So that's what we needed, but we also see that it does not come immediately. It's a set of differential equations that you would have to solve. So it depends really on the kind of problem that you're working on, whether that's going to be easy from an analytic point of view, or whether you will have to rely on numerical tools to solve these equations. So if I just go back, what I did here is I took the limit for h running to 0. I recognize here the derivative with respect to t of tpxij. And if I take the limit here for h running to 0, then I get rid of the little o of h term. And then I'm left with this sum over k that you see over here, the tpxik, the mu kj, and then minus the tpxij and the mu jk that we put on the final sheet over here. So this set I can use in any multiple state model that I want to consider, but it's more complex, of course, compared to the expression that I had in the previous example with the permanent disability model, where no transitions up and back are possible. But this is a very general set of equations that I can work with. Yeah, and we're going to see in the examples to come how to treat this from a numerical point of view. Yeah. So this is important, and do keep in mind that for the sojourn probabilities, that we already had a set or a fairly general expression, and that was the derivative with respect to t of tpx ii bar was equal to this guy. Voila. So such that for this one, we know what to do, and we can bring this guy to the other side. Then we recognize the derivative of the logarithm. Then we can work with that, and we ended up with this exponential of minus the sum of all the applicable transition intensities over here. Yeah, so that's what we had earlier on as a solution, of a very explicit solution for the differential equations that hold for the sojourn probabilities that you see over here. Yeah? So if I take the two together, then I've got the whole framework that I can work with for any multi-state model that I want to consider. Or that's what you recognize over here. So if I go back to my sheets, if I look at expression 7, for instance, then you'll see that this is exactly the set of differential equations here that we derived on the iPad. And if I put that together with the differential equation that I already had for the occupancy probability, then I get the whole framework to handle, to deal with. Right? So what are the ingredients here? You'll need the transition intensities, and then you'll have to solve this set of differential equations, either analytically, either numerically, in order to come up with your transition probabilities. Okay, so that's what I want to illustrate now in the final sheets for today. So section 8.5 from the book is then going to look at some numerical evaluation of such probabilities. So let's see what we can do over here. Yeah. So we take a strategy where the transition intensities are known or are assigned. That is sometimes also called the transition intensity approach. And so that means you estimate or you somehow get a meaningful value for these transition intensities. And given that you have those, you're going to go through your calculations to go to obtain expressions for the transition probabilities. And that's the strategy that we outline here in the second bullet. So actuarial practice should then be estimate these intensities from data, compute the transition intensity, compute the probabilities from these using a set of differential equations, the number of equations. Yeah. Now, of course, the calculation of such probabilities may be a complex integration problem. Under certain simplifications that we will see in the next weeks, solutions can be achieved easily. If that's not the case, you will rely on numerical techniques to calculate your transition probabilities. Yeah? So let's do some examples, and I'm going to start here. So we're going to work with the permanent disability model. That's the first example from the book. And we're going to assume that the mu01 is constant and given, the mu02 is constant and given, and the mu12 is equal to the mu02. So you immediately see that this is not a very valid assumption, because the transition intensities, they are constant for all ages. You have the same force of mortality from the healthy state as from the disability state. That's the assumption over here. So this is not very realistic, but it's a nice example to start with and to make sure that we understand how to calculate probabilities like the ones that you see over here for this model. Okay, so let's do first the P00. Yeah? Imagine we have a 60-year-old and we want to know he starts at time 0 in the healthy state. What's the probability that he will still be in the healthy state 10 years later? Yeah? And then we're going to ask ourselves a similar question. If we start with a healthy life, age 60, what is the probability that he will be in the disability state before age 70? These are the probabilities we want to catch. So what are we going to do? Well, first of all, you know for this model that the occupancy probability is equal to the probability without the bar, because if you start in state 0, if you have to be there again in 10 years from now, then the only scenario is that you just stayed there, right? So if we look at the TP6000, then that is the same, at least in this model, as the TP6000 with a bar. And of course, for these sojourn probabilities, we have these easy expressions. What do? We take the exponential of minus the integral from 0 to t of the sum of all transition intensities that are applicable to our policyholder. Now, if you have somebody in state 0, then 2 transition probabilities are applicable to him or her. That's the intensity to go from 0 to 1 and the intensity to go from 0 to 2, right? So that is the sum of 2 constants. You see them over here. You can work out this integral. That's very simple. And replacing the t with the value of 10, you get the number, you get the probability that was requested. So that would be the answer to our first question. Simple. We only use we rely on the expression for the sojourn probabilities here. Okay. If I continue then with the other probability that was requested, so that's the 10P6001, what am I going to do here? Well, the expression that I want to evaluate now is the one that is printed over here. Yeah, because I know I need to go from state 0 to state 1 in a period of 10 years. But I know that there is no going up and back possible in this permanent disability model. So I will go for the very simple approach to calculate this transition probability. And that means at a certain point t, yeah, I will make the switch, the transition from 0 to 1, and then I will stay in state 1 for the remaining time length. Okay, so at a certain point t in between 0 and 10, I'm going to make this transition from 0 to 1, and at that time I will have age 60 plus t. So I get this expression over here. That's the one for which we needed to do all these different steps in order to come up with this expression. Now, of course, the mu01 that you need, that's a constant, that's given. For the 00 and for the TP6000, we derived an expression on the previous sheet, so we can plug that in over here. And then, of course, for this latter expression, you have to think again. That's what we do over here. How do I get this probability? That's the probability of staying in state 1 in the permanent disability model. So that means I've got again the exponential of minus an integral of all the applicable transition intensities. Now, if I'm in state 1 in the permanent disability model, then the only possible transition is from 1 to 2, right? So I'm going to use this mu x12, which in this case is equal to the mu02, so that's the constant that you see over here. And I have to take into account the duration of the time length that I want to consider here. Yeah, so that's what I'm doing. I get again a nice expression, I plug that in. I need to do the integration here. This is a toy example. This is something that I can solve with pen and paper. This is just an integral of an exponential function. All right, any questions here? So this is what I did. I essentially used two of the formulas that we derived along the way today. I plugged in the constants, worked out the integral that gives me the requested probabilities. Good. Now we're going to make it one step more complex. And we're going to say, well, our transition intensities, these are not constant. These are certain given, there are certain functional forms given for these transition intensities. Yeah. So in reality, this is also highly unrealistic that you can come up with these nice expressions, but let's assume for now that these are valid. So I want to calculate the same probabilities. TP6000, that's the same thing. I need to take the exponential of minus the integral of all the transition intensities, which are applicable to somebody in state 0, right? But now, of course, I've got more complex formulas, so I have to plug in these functional forms that I have over here. Same for the probability to stay in state 1, yeah? And either you're going to solve, well, here at least you can work out the integrals analytically, so you can play with these expressions. And apparently, this is the result that I obtained after working out these integrals. Yeah, so here that's still doable. But if you look at the probability to go from 0 to 1 in an interval of length 10, yeah. Then again, you have to bring in all the formulas and you're going to end up with something that you can no longer solve analytically, but that requires numerical integration techniques in order to do the calculation for you. Yeah. So the transition probability still has quite an accessible form because we're still in this permanent disability model, but I can no longer do the calculation pen and paper because if I combine these three quantities here in the integral, and if I'm asked to do the integral, then I say, okay, that's too hard. I need numerical integration techniques for that. Yeah? And we're going to illustrate that later on in the computer tutorial, but that's doable. Okay. Questions on this? So this is my permanent disability model again, but now it's slightly more complex expressions for my transition intensities. There's one final illustration to cover, and that is what if I make the switch from the permanent disability model to the general disability model, right? So now I have transitions from 0 to 1, from 1 to 0, from 0 to 2, and from 1 to 2. So I need 4 expressions for my transition intensities. The question is the same. Calculate the probabilities. The probability that given that you start in state 0, you're again in state 0 after 10 years. And the probability that given that you start in state 0, what's the probability that you will be in state 1 in 10 years from now? Okay. So what I will have to do now is I will have to rely on my Kolmogorov forward equations. So I'm going to start with my differential equations as we derived them in this last part of today's class. And I'm not, well, what I'm doing here is I already rewrite the differential. So the differential over t with respect to t of tpxij, I already rewrite it such that I get an expression that I can work with in a numerical, in a numerically simple way, let's say. Yeah? So this is what we derived in formula 7. Okay, you recognize the differential here if you would bring this guy to the other side, if you would divide by h, and if you would take the limit with h running to 0. That's my Kolmogorov differential equation system. Yeah. So what I need to think about now is which transitions are possible. So if I start here with I and j equal to 0, both equal to 0, then ij is equal to 0, 0. And then I have to think about which transitions are possible out of state 0. So then I have to work with mu01 and mu02. Okay, if I put here I is 0 and j is 0, then is there a state k possible such that I can go from state 0 to this state k and then return to this state 0 again. And then the only intermediate state k that is possible is state 1, because I can go from 0 to 1 and then again from 1 to 0. So I've got this possibility over here. But do note that I cannot use k equal to 2, for instance, in this expression, because the transition intensity to go from 2 to 0, that would be equal to 0, because that would be the transition where you go from the dead state back to the alive state. So that's not possible over here. And then in a similar way, you look at the probability 0, 1, right? So you start in a healthy state and you will be in the disabled state after a certain period of time. So here you work with, again, with the Kolmogorov equations, but now I refers to state 0 and j refers to state 1. So you plug it in again and you look at, okay, which transition intensities are possible, and you write down the expression. So then the only thing that it remains is, how can I work with this in a numerical way? And in this course, we're not going to use very complex numerical methods to work with this set of differential equations. We're going to take a very heuristic approach where we're going to say, okay, let's start with a boundary value. So for instance, 0p, 0, 0. So that's the probability that you will be in state 0 at time 0, and that you will be there again in an interval of length 0. So that condition is equal to 1, because we're going to start with a healthy policyholder. Yeah? So this value is equal to 1. And on the other hand, 0p, 0, 1, that's going to be 0, because you can only occupy a single state at time 0. So using these boundary values, what we're going to do is we're going to take small steps, and solve these guys then numerically, using the constants or using the expressions that are valid for our transition intensities. So essentially what you're going to do is you're going to work with a raster like this, where you start with t equal to 0, where you move in small steps. So here we go in steps with length 1/12, and we move until t is equal to 10, We fill in our expressions. So we start with the boundary conditions here. We start with the given expressions for the transition intensities. And we use the expressions that you see over here to evaluate the transition probabilities in each considered time step. Yeah? So that's a very simple way. It's the Euler method to evaluate these differential equations in a numerical way. So you can do way more complex things, but for now this is sufficient. Okay. Any questions? So in the examples that we covered, we went from the most simple multi-state model to a more general multi-state model where transitions up and back were possible, and where in the end we needed the Kolmogorov differential equations to say something about our transition probabilities in a numerical way. Yeah. Okay. Any feedback or any comments? If not, then I'm going to wrap up here. So what did we do today? We introduced the concept of multi-state models, relevant notation for transition probabilities and transition intensities, and we focused on getting useful formulas for these transition probabilities. And then we illustrated eventually these formulas on the permanent disability model, where no transitions up and back are possible, and then the more general disability model, where a transition between the active and the disability state is possible. So what we're going to do next week is how to value insurance products using the probabilities that we put together today. So we want to be able to calculate premiums, to calculate present values of products, and so on and so forth. We want to be able to calculate policy values, so that will be the next step to cover.